传遥歌与空号Rizki Jana Dean Tuna Maxim Okay, on Monday, we tried to show the received power in the logarithmic unit with for the propagation of a channel. So it can be expressed as the received power with respect to distance. It can be expressed as we detect the detected power at the distance from the transmitter over 1 kilometer minus 10 times n times log 10 c with unit kilometer. Okay, and also we add another term. So this one is the 1 kilometer. It can be for the, this is for macro cells. If it is micro cells or with a short range, it can be 1 meter, 10 meters, or 100 meters, something like that. And the parameter n here is also called a power decay law. Okay, and this term, it is called the Gaussian random variable, okay? And 0 is its mean value, alright? So if we take the area of the whole power, received power, that means this term is going to be 0 because its mean value is 0 and the standard deviation is sigma L. So if we take this term, then it becomes 1 kilometer minus 10 times n times log 10, the distance in the unit of kilometer here. So here we need to consider one point. So what's wrong? Oh, sorry. So when we here we take a reference distance as at the distance from the transmitter from the transmitter is 1 kilometer, right? So here this one it cannot be a definite distance, right? Because we have a reference here. So this distance actually is 1 kilometer. But here we deleted because we converted our distance d. It's also in the unit of kilometer. It's divided by 1, so it is still itself. However, if we change this distance to maybe 100 meters, then this side should be divided by 0.1 kilometer, like this one. So this is a relative distance. It's relative to the reference distance for this reference power here. So that means when we wanted to calculate this part, it becomes divided by 1 kilometer. So if we take it in a much more general station, if for example this distance is r, so if we take the reference at position r here, so it becomes minus 10 times n times log 10. This is r divided by capital R with respect to the reference distance here. So these two terms are related to each other. So this is what we wanted to point out here. So Now, when we consider the shadowing concept, so for today's class, we wanted to introduce as the coverage or the interference under the influence of the shadow effect. So previously, for the last week, the first time on the channel modeling, we introduced there are 3 different rates of the variations. All right. So, for example, the variation can be power variation. Can be 3 kinds, right? The first kind is very slow and fast. 3 terms. The very slow variations is usually related to what? Do you remember? Yeah, free space path loss. Okay. And the slow variations is related to the, as we introduced on Monday, as shadow effects, right? And the fast variations is usually related to multipaths. And so when we want to concentrate on the shadowing effects more, sometimes what we usually do is using maybe a filter to filter the fast variations away, alright? To more concentrated on the shadowing variations. So this is what we wanted to do. So another time that we usually used to compare the series or the signal series, and it is usually generated, for example, in the simulations. And we really need to set a performance threshold to let our work more concentrated on it, especially in the noisy or in the interference limited signals. So here we get a plot. So we show a plot to concentrate on that. So the axis is related to the received signal. Received signal variation range. In dB. Okay. And so now we want to take the calculation or the analysis on it. So firstly, what we have is, if for the receiver, there should be a receiver threshold, alright? So if we have the signals, for example, it is really multipath. So then maybe it's like this. Okay. And first thing is we set the receiver threshold, alright? So that means below this or this thickness, so we can get that above it. And also, if we take the multipath, shadowing the multipath, firstly the fast variations on that. So what we need to consider is we should have a multipath region, all right? So for example, if we assume this curve is the really multipath, so here we take the really multipath and we do not consider as the right multipath. So Now, if there is also the shadow effect, so the shadow effect is also that has much higher. It has a higher receiving power. It's a different color. This one. So this is the shadow. And we use the very common distributions, log normal. Okay. So now, if we wanted to consider the threshold for the multipath, and so it should cover this region, and we said we add the multipath margin on the basis of the receiver threshold, so the threshold is increased, especially under these regions. So after that, if we want to consider the shadow effect, all right, set the threshold for the shadow effect. So this is the shadow margin. The shading margin. So the shading margin is really considered as the non-normal distribution, and it is also under the addition on the threshold and the multipath margin, and then we add another margin, shading margin. And this curve, this line actually is is usually related to the area coverage. So if we wanted to see the coverage of the base stations, the coverage area of the base stations, the coverage areas with that one, and sometimes we need to send the fringe on the cells, right? So the area coverage need to be considered. So this area is also according to this line above it is the large area average power. So this one is large area average power here, according to this line. And the shading part is really caused by maybe some large, big, or significant obstacles caused by that. So this is the threshold, the performance threshold we needed to consider when we wanted to do the calculations on that. And so now we come back to the coverage areas. So when we read some references, really, for example, we have a base station here, for example. So its coverage area is usually expressed as circle, right? So this is its coverage circle with the base station at the center of it. So sometimes when we wanted to do the analysis, and when we want to design the coverage of the base stations, it should have several kinds of the coverage areas. So for example, a larger one, like this. And it can also be a different, maybe much larger. So mathematically, how we could see the coverage of the base station if we consider the received signal as follows the log normal distribution, and we really set what? We already set a parameter to set that, right? So, for example, we set the percentage, what is called the percentage of locations. So, if you read some references, you might see some, for example, the coverage is maybe 95%, and for this line is maybe as 90%. And for this line, maybe as 50%. So this is the coverage of the signal. If it enters this fringe, so all this line is called fringe, enters the fringe corresponds to 95%. That means we can say, okay, and can accept the power is related to 95% average. So that means, for example, if it follows a Gaussian distribution, if this is the probability, like this one, all right, Gaussian distribution, this is maybe x average, and we wanted to get, for example, as 95% average coverage, so that means the signals may be higher than this value, okay, as a value that is, it can reach to 95% of its signals can be obtained. So all these areas. So this is just mathematical expressions for the area coverage. So, for example, if it enters this area, so that we can say is coverage to 95%, and if it enters this area, we can say, okay, as 90%. How about if there is a mobile user, it moves around the fringe between 95 and 90. If it moves along this fringe, along this circle, it moves. So what it can be? It receives the power. As it can be 95% or it should be 90%. The coverage. Think about it. So, if we can express it, for example, it moves from for example, it moves from this point, okay, and we set this angle as theta. This is theta. Theta move changes from 0 degree to maybe a circle, so this is 360 degrees, all right? So the threshold for it is 95%, all right? So it receives power what it should changes, how is the variation of it. So it really oscillates on both sides of this threshold, and like this one, okay, and it oscillates like this one, oscillates this one, oscillates like this one, oscillates to both sides, and so 90 be 180, can be 270, then finally it's 360, So it oscillates. It is sometimes can be a little bit higher than that. Sometimes it can be lower than that. So its coverage is not a constant. It varies between both sides and oscillates between both sides. So this is what we needed to do. For example, we needed to keep the coverage area for example, we have multiple cells to cover one area. So when there are several maybe superpositions between several cells, usually 3 or 2, right? So this area coverage is needed to be analyzed seriously, for example, to make sure that its coverage should be uniform, right? So this is the coverage, the expressions for the coverage. And if we wanted to express it mathematically, for example, if we have, for example, the base station here and the user is located here, the distance between each with the base station is r to represent the distance. So the first thing is the area coverage probability. We call it FU to represent it, the area coverage probability, FU. So that means it should be the probability means it should be a fraction, all right? So the fraction is something divided by area of the circles, right? The circles. So this part and for the what thing should be divided. So that means the signal levels inside of it, the signal levels exceeds one value. So for example, the signal levels exceeds X node. So we set the threshold is X node. And times the area integration. So this part, the px node, which should be probability also a function. So it can be px node. It usually is the probability of x values larger than x node. The x node is the threshold. Okay, like this one. It's related to this one. So accordingly, if we wanted to take some calculation, so we need to get an exact expressions for the px node. All right. So px node, the x or x node represents the x node is threshold for the power, right? So the x is the received power. So that means the px here should be a function related to it. And according to the for the slow variations, we take the log normal distributions or the Gaussian distribution. So the px node or px has expressions in the Gaussian distribution. It equals square root 4 pi sigma L, right? Then the exponential minus x average square divided by 2 sigma L squared. So this is a general expression for the Gaussian distribution, right? So this one is the standard deviation, and this one is the average power of the receiver. All right. So now, when we wanted to get, for example, the come back to get the expressions for this equation. So we first get the expressions for px node. So px node can be related to p node, x node, px node, and also add the distance r. So we get capital R to express it. It becomes probability x larger than x node, alright? So it means larger than x node, that means it should be larger than x node to infinity, alright? So then this is the Gaussian distribution of x and dx. Alright, so for the Gaussian integration of the Gaussian distribution or the Gaussian function, we can convert it to error function, alright? So that means x node to infinity 1 over 2 pi sigma l e minus 2 sigma l squared x minus x squared dx. So for the error function x, it can really be expressed as 2 over square root pi times 0 to x e minus t squared dt. So that means this term should be separated into two terms, 0 to infinity minus 0 to x node, right? So 0 to infinity for this function, the probability, so that should be half, alright? Minus infinity to infinity should be unit, just 1. 0 to infinity becomes half of that. And also, there is another term as the x node to the 0 to x node. So it becomes half of the RF, and this is the x node minus x average divided by sigma L square root. So take the very transformation of the variables and can be expressed by this one. So this is the expressions for this one. And also, if, for example, we take a condition, for example, the expressions for this part. This is x variation like this one, the same thing. And this is the x average, right? And the threshold here is x node. So the probability of this equation, the final value of this equation, should be, this part is half of it, alright? This half. And the integration part, the area of this part is related to this term. So add them together and we get the total probability of the coverage. So now if we have, for example, this is the average value, alright? So average received power, it should have an expression on it, alright? Just an shadowing effect. And the turn effect with this. With its received power can be calculated as how much? Do you remember? Okay, if there's no shadowing effect, just in free space, for example. As we demonstrated previously, right? Be expressed by this term, average power, right? So this is average power. It can be expressed as, for example, R for generally minus n times n log 10 related to this part, all right? So alpha is the reference, the power received power at the reference point, okay? And so we can add this term into the equations here. We can add it into here, substitute this term, and then we can get the expressions for the probability. So we want to calculate the probability of the power received with the threshold x node, and its position is r. For example, it can be expressed as half plus half the error function, and inside is the expression sigma L square root 2, alright, times x node minus x average, alright, average is alpha minus 10 times n plus minus log 10 small r divided by k to r. Okay. This one. Okay. Then we want to take the integration of the whole area, so the area coverage probability. Is the FU, right? FU. It can be expressed as 1 over pi r squared. So take the integration a x node r the time the area integration. So as we said that the covered area is usually a circle, right? So the for the polar coordinate system, it can be expressed as r, the r times the phi, all right? Expressions by this term. So, if we wanted to calculate this part, and we consider that the px node is only related to the radius or the distance between the user and the base station, right? So that means on the angle range, it can be separated out and is 2 pi divided by pi r squared, and this is r, right? So this is px node r and r dr integration of h. And finally, the calculation is a little bit complicated, but yeah, we should get it. This half long term 1 minus a plus the exponential function divided by b squared times 1 times 1 minus r, okay, 1 minus ab divided by b. This one. And here, to simplify the equation, we used a and b parameters related to x node minus r divided by sigma L square root 2, and b is equals sigma L times square root 2 times 10 times n log like this one. So this is the expressions for the finally area coverage probability for this equation. From here, I think we cannot get the maybe a general understanding on its evolution, right? So if we wanted to plot it and express that as lines, and we can get a much more general relationship, the general relationship with respect to the P X node R. For example, here this is the threshold for the fringe probability values, and this one is the area coverage probability FU, and here is set the standard deviation divided by the propagation power law, the power decay law. So previously the maximum point should be if sigma L divided by n, or sigma L equals 0, the standard deviation is 0. That means the area could always be covered, right? So the 100% be covered. So that means the maximum point should be 1 here. And when the sigma L standard deviation varies, for example, as area coverage probability gonna decrease, and the minimum for the coverage is usually depends on something, right? So it usually depends on the threshold that we choose, right? So for example, if we set a threshold X node R as 50%, then it should be lower, right? The coverage area maybe it can only be finally coverage area related to here is maybe it's just 60%, maybe, for example. If we increase it to, for example, 70%, then this coverage area becomes slowly, like here, 70%, and it's related to maybe here, area coverage can be 80%, and when we further increase it to be maybe 90%, set it, and that can be maybe reached to 95% the coverage area. So this is for the expressions for it here. And there's another thing that we needed to take care as the location variability here, the sigma L, the standard deviation, or can also be location variability value. So this one, it can ranges, it usually set, it ranges from 5 to 10 dB in the wireless communication speed. It varies in this range, so it usually cannot be in 0 actually. So that means it's analyzed areas maybe is in this range is 5 to 10 dB for sigma L. Logarithmic scales this area. And also sometimes what we needed to consider is, so the coverage cannot, this is just a theoretical analysis on that, and actually when we consider the mobile coverage area for the analysis, we should consider an important parameter. It's related to, for example, for example, the usage of this location, right? So it's related, for example, for in the suburban or the urban or the rural areas, the value is going to be a little bit different. So it also considers the terrain database. It can be T, D, B, abbreviation. So this is usually used for the radio planning purposes, and the coverage calculation should be performed. So, for example, if our coverage area is too large, all right, if it is too large, and it covers different kinds of terrain databases, so the calculations on that one cannot be used, all right? It can vary according to the usage of this area. So we need to scale the terrain databases, and we need to confirm, or we need to stretch the analysis of the cell sizes, So the cell size should be really smaller than 100 meter times 100 meter. Like this one, or smaller. And typically, for the prediction pixel sizes, we already set it to be 50 meters times 2 meters as the cell size. So why we choose such kind of such a small one for the analysis? This is commonly used. Okay. So there are several kinds of considerations. The first one is definitely the resolution. All right. So this 550 times 50 square meters, the pixel size, it can provide a relatively high level of details in the representation of the terrain. So very high resolution, relatively high resolution for the characterization of the terrains, and also can get the enough signals, enough details of the terrain. Actually. And also another thing is accuracy. So the such level accuracy with such a kind of the pixels is really acceptable for the design or for the practical radio planning purposes. And this is the on the respect of the resolution. The second consideration that we wanted to needs to consider is the because we wanted to scale, or we wanted to take planning on that one, we need to consider the computation. All right, the computation efficiency. So this computational if we reduce the pixel size or the cell size, we can get much higher resolution on that one, all right? But it can the assumptions on the computing resources gonna be another factor that we need to consider, and also the computing speed that we need to consider, right? Especially for high-speed mobile users, and the computation speed should be important factor that we need to consider. The third one is the compatibility. The compatibility is usually related to the standardization. For the commercial usage, and so it should be compatible with the international standardizations on that. and also it's related to, if we want to get the information of edge, it's related to the data availability. The data availability, right? So it's compatible with this. It's just in the format that international standard. Okay, we're gonna come back later in 5 minutes. Okay, let's continue. So we choose the fixed cell sizes, and we can also, so
we separate the areas to be many pixels, and finally we take the area of them to get the whole area of that one, coverage information on that one. And so how we could define, previously we said that we chose the expressions for the area power like sorry. So we take the area power by this equation, right? So this is just a much general expressions for the just based on the distance between the base station and the mobile users. And if we wanted to consider much more details about the terrain, so we needed to separate the we need to have different expressions for the powers for that. So, for example, there is one model on that one. It is called Hata model. So the Hata model is the first thing is, firstly, it is proposed by a guy named Hata, and it is based on the measurements by another guy, a Japanese guy, Okimura. So it is based on this one. So this model is usually, I think, maybe sometimes you are barely can consider can listen the Hata model, but it is more generally about this model. So it is usually the one part of the Okimura model, and this model is can usually used by the commercial model and is cost. The cost. This one, the cost model. And as we previously mentioned, theoretical models for this one is there are two groups models, the two classifications models. The first one is proposed by ITU, right, the International Telecommunication Union, and another one is cost. It's related to this one. Okay, now the pop loss between both isotropic antennas. So we do not consider the antenna gain inside of it, right? So it depends on the specific designs of the system, right? So we just consider a general conditions and with an isotropic antenna. So for the for example, the area for the stations or the scenarios or the environments, maybe it can be urban or suburban or rural areas. We just have three kinds. Urban, so maybe there are many against the buildings inside of it, right? And the suburban, and maybe the buildings is not so dense. And also the rural area. So we usually separate it to be such three kinds of environments. And so the first thing is for a flat urban area. So flat, okay, there's no mountains, and there's only a flat area with many maybe buildings on it. So the pop loss in the logarithmic scale can be expressed as, first thing is it should relate to there's constant plus 26.16 logarithmic f frequency related to minus 13.82 log the antenna height of the base station, and minus another parameter, a correction parameter related to the mobile users, and also there is another term is related to loss. This term is 44.9 minus the term related to the height of the mobile users of the mobile user, the base station, the height again, and related to the distance between the base station and the user. So this one is related to the antenna height of the base station antenna height of base station. HM is antenna height of the mobile users, and AM and A is related to the height, but it is a function of that one. So, and for example, if HM is smaller than maybe 1.5 meters, it can be related to 0. So now, if we want to set, for example, this is the environment dependent. So if this is just for the urban area, and if for example, a large city, and there are several kinds of that. For example, for the medium to small city, can also be to the suburban area and also rural areas. I'm going to use that in the next page. So for the large city, the expressions of HM, it has its own expressions. The first expression is frequency dependent. Smaller than 200 megahertz, can be larger than 400 megahertz. So it has its own expressions. It's 9.29 logarithmic 1.54 HM squares, like this one. And if it is larger than 400 megahertz, it can be 3.2 times logarithmic 11.75 HM squares. So it has its own expressions for the large cities. It's frequency dependent. And also for the medium to small cities, the AHM, it also has its own expressions. So it can be expressed as 1.1 times the frequency. So minus 0.7 and times HM minus 1.56 logarithmic frequency minus the 0.8. So it's a frequency dependent, these things. And the frequency part is inside of this equation, this expression. So this is for this one. And here we can see that this model is frequency dependent, but usually the thing is because all these values are obtained based on the measured data by this guy, the Okumura, this guy. So he conducted or he obtained the expressions just by the fitting to the measured data and get the exact values for these parameters. So that means this model is much more station or location determined, right? So even though this is for the urban area or for the large city or for the medium small city, I think all the large cities, they are different, right? So it's also we should, if we wanted to get the exact predictions or analysis in one specific city, so for one specific city. So we needed to correct all these parameters based on the your own exact or specific measurements in that city. So this is for the urban area, and also there are expressions for the suburban area, and also for the rural area. It has its own expressions of that one, but here it will not change with respect to the height of the mobile users' antenna. It's just related to the could get the expressions for the path loss minus 2 times. Two times log 10, the frequency divided by 28 square minus 5.4. This is for the suburban area, and for the rural area, it equals the of course the loss calculated by the minus 4.87 f square plus 18.133 f minus 40.94. So this is for the rural areas also. So as we said that these things are always frequency dependent, and as we all know that when the usage of the electromagnetic waves, it transfers from the lower frequencies, from the radio frequencies to the micro, to millimeter, to terahertz, to the optical. These models should always be changed, all right? It should be all these models cannot be consistent for the whole electromagnetic frequency spectrum. So it has its own specific usage. It's for the specific frequency range. So for all these frequency ranges, its usage is larger than 150 megahertz, smaller than 500 megahertz. So it can be used for this range. And also it has its limitations on its antenna height. Also, it should be larger than 30 meters, smaller than 200 meters at the for the base stations antenna height, and for the mobile users, should be larger than 1 meters, smaller than 10 meters, like this one. So it's more commonly used, and the distance in kilometer should be larger than 1 kilometer, smaller than 20 kilometers. So this is the frequency range for H. And for example, if we want to use the calculator for the GSM signal, so for the third generation wireless networks, right? So its operating frequency is definitely 180 megahertz, for example. And also for the PCS, for example, its operating frequency is 1900 megahertz. All these models have not been used actually, and we needed to modify the HUT model. Modify HUT models on that. So there's another model. It's called, I think you can try to Google that, coast model, and it has its own 3-1 HUT model to calculate on that. So for an example, if we have several buildings, and in the urban area, for example, we usually set our base station on the top of the building, all right? So on the top of the building and always on the tallest top of the building. So, and we have many buildings inside in this city, many buildings. This one, also this one, right? And if this is the base station here, and we have a car. We have a car on the road, moving on the road. So if we wanted to get the received power, calculate the received power by the car of this car as the mobile station, mobile user. So we need to consider several kinds of the effects, right? So the first thing is we need to consider the free space population, right? This is definitely for any kinds of predictions. This term is definitely there and should be considered. And the second thing is, as we previously mentioned, Monty, is the diffraction, all right? The diffraction by these buildings, all right? So because we have, even though here we says, okay, the diffraction occurs due to this building, and also definitely all these buildings, they should, the diffraction effect should always be considered. So this term is called the multi-screen diffraction, or the diffraction loss. Diffraction loss, all right? So we consider as the obstacles to be screen, and for the buildings we can consider as absorbing screen, all right? Definitely an absorbing screen here. So add this term, and also there is another term. We want to see, so here, this is the roof, okay? This is the roof, and the roof, and the roof, and the roof. So from the roof to the street, from the roof to the street, from this roof to the street, from this roof to the street, all these things, they are also another term of the diffraction loss. So it's roof to the street, diffraction. So these three terms should be considered. The first term is the free space, all right, to here. The second term is the multi-screen diffraction from this roof. The third term is the roof to street diffraction. So all these three terms together and get the total power loss, or the total propagation loss of this of such a link for when a mobile user is moving inside of an urban area. So this one now, and so we wanted to take the analysis on such signals. So what should we do actually? So first thing is we generate maybe a signal, and with the path loss and with the shadowing effects, we get rid of the multi-path effects as the fast varying signals. So we just consider the path loss and the shadowing effects. So now, if we generate all physically generated or actually generated signal, it's usually a random, right? So the first thing is we generate a random signal. So for example, if we have a signal here, it is randomly generated here, and if we wanted to check analysis on it, the first thing is we hope it can be correlated. So that means if we wanted to design correlation algorithm onto the signal at the the signal transmission processing side. So the first thing is we really consider as we add. So the signal comes first, and then it's gonna be added by a term. This term is called the added. Actually, just need to term. So this term, it comes to itself actually. So this term has come from itself actually. So and here, but there is a delay on it. So this is the S, a delay H, and then multiplied by a parameter A. So one part of it itself is delayed by ds, and then multiplied by parameter A. They come them together, add them together like this one. So and current to the after it is added to the current input symbol, and the expressions for AS can be expressed as expression of the minus S, the delay, and also the correlation length. So the correlation length is usually, as we previously mentioned, for the rough surface. All right, the characterization for rough surfaces, we consider the RMS height. All right, the roughness characterization on the y-axis, and also there is another horizontal characterizations on the horizontal scale. It's called the correlation function, right? And the correlation length. Here, this correlation, because we wanted to correlate the, we want to keep the signals to be automatic or to correlated, yeah. And so we add this term, the correlation length here, and the correlation length can really be smaller than the sampling distance, right? So when we take the signals with respect to a distance, so that means the distance sampling range, or the distance sampling rate, it should be considered here. So this term is smaller than that value, and it can be sometimes. It's really for a scenario dependent parameter, and it usually changes from maybe several meters to several tens of meters, depending on whether it's urban area or the suburban area or the rural areas of that. So after this term, there is another term. So this is multiplied by another term. It is called B. So B is also introduced for the location variability also. So it can be expressed as, so because it's a location variability, so it's related to signal L times 1 minus A squared. And after that, longer, like it to be longer, like this one. And we added another term, is M. So this term is added because we wanted to switch, or we wanted to move the correlated or uncorrelated random signals away on the signals on the expression or on the plot. And after that, because the generated signal may be as in a logarithmic and so this is the final power. Now we transfer it to the linear scale. Okay, transfer it to the linear scale, and this is the finally obtained power level here. So after that one, if after such a correlation analysis, so usually if, for example, we have the, for example, we generate a random signal like this, for example, just one example, and after the autocorrelation, maybe the changes uniform like this one. And we get signals are much more precise like this. And this is just one kind of the method for the autocorrelation. And also we can have several kinds of autocorrelation methods. One of that is called interpolation. Alright. This is only useful when our distance sampling rate is not very high. For example, we take the measurements and just based on the sampling rate is just only equals the correlation length, for example. And this is the uncorrelated log normal samples. And if we take the interpolation, maybe we can take it to be, you know, the interpolation, all right? Like we add more details on it. More details on it. Add more details on it. And this is another kind of interpolation, the autocorrelation, the correlation. And we can get more information about this signal. So this is the correlation for the signals, the series with the correlation. And also there is another method is we wanted to take the transferring of it is the transformation. Algorithm. This one is transformation algorithm. So 1 minus a theta minus 1. So this is the third, the general expressions for the transformation methods like this one. And so the correlation, the signal correlation is really important because as we know that if when the car or when the mobile users at most on the fringe or on the contour of the coverage area, with both coverage areas, 90%. As we know that is signal is correlated, all right? So it oscillates between both sides. So it needs autocorrelation on that one and for the data processing of that. So all these things now is for the shadowing effect, and the shadowing effect is usually caused by the large obstacles, right? For buildings, for if at higher frequencies at millimeter wave range, is due to maybe the human body or the doors, something much more smaller things, and its analysis should be a little bit easier than the multipath components, right? For the multipath components, we need to consider many kinds of parameters, such like the time delay, the power expansion, and also the angle of arrival and the angle of departure, and many parameters should be considered inside of it. So it's going to be what we wanted to do next week. And so now I think we're done for today's class, and I'm going to see you guys next week. Okay? And the next week should be our last week, all right? For that one, and after that, we're gonna give you the final homework next week, and then we are done for this course. Okay?黑走了，黑走了。
我早就在我们实验室隔壁，我直接过去热死。
说掉了。
我昨天画了个图，没成那匹马。但是你说要那之后要调往上调的话，
因为他们这个商业化，那应该还没有到。
对，没到太
交代他们做高频的没有做，都是偏低频一些。
对，
他们主要是做低频的那个轨道交通的那些，高频的因为他们觉得轨道交通用不上去。
之后咋办呢？
之后的话，再调tempo，但是我觉得其实100和200其实差别不大。你在整个频段，虽然说100到200之间差了100吉赫兹，但是100吉赫兹的那个传播特性和200吉赫兹，我觉得差别不大。你想它的100波长是3毫米嘛，200的话才1.5毫米，就是它只是它那么一半儿。所以它传播特性差别不大。
行。我先走。
来，这边。
When will we have our presentation?
Oh, the presentation, I would hope you can just maybe take a video and just send it to me.
Okay.
I would not do the presentation in the class because I needed to finish all my notes on that in the class.
So okay. Will be recording the
Yes, you just recording the video, maybe 10 or 15 minutes and then send it to me and I can see that. Okay.